Hello everyone. Today I will give you a detailed explanation of how to design an automatic impedance measurement processor using an MCU. We will start with a relatively rough initial scheme, gradually analyze its shortcomings, and finally present a fully optimized and precise implementation. Through this sharing, I hope to help you gain a deeper understanding of the principles of impedance measurement and the advanced applications of MCUs. This presentation is divided into 4 parts. First, we will analyze the original scheme proposed by other engineers and identify its problems. Next, I will elaborate on the optimized solution we have developed. Then, we will dive into the core technologies used in the optimized scheme, such as DDs and synchronous sampling. Finally, we will summarize the content and share some key considerations from the implementation process. Next, let's take a look at how to comprehensively revise and optimize this solution. The idea behind this original scheme is as follows. First, a square wave is generated by toggling the GPIO pin via a timer interrupt. The square wave is then shaped into a sine wave using a bandpass filter and applied across the resistor under test. Next, the returned current signal is conditioned and amplified by an operational amplifier, and an absolute value circuit is used to flip the negative half cycle to the positive half cycle, converting it into a pulsating DC signal. Finally, a low-pass filter smooths this pulsating signal into a stable DC voltage, and the MCU calculates the impedance by sampling this DC voltage through the ADC. While this scheme is workable, it has numerous drawbacks that result in low measurement accuracy. Next, let's see how we can fully revise and optimize this solution. Our optimized solution includes 3 major improvements. First, we abandoned the method of toggling GPIO via a timer and adopted DDs technology, namely direct digital synthesis. We transfer pre-stored sine wave data to the DSE through DMA, which generates a sine wave with highly precise frequency and amplitude. Second, we removed the absolute value circuit and instead used a DC bias circuit to add a DC offset to the AC signal, keeping the entire signal within the 05 VADC sampling range. Third, and most crucially, we applied synchronous sampling. The ADC and DC are triggered by the same timer to ensure sampling synchronization. Sample data is stored directly into memory via DMA, and the true RMS value is calculated using an algorithm, which greatly improves measurement accuracy and speed. How exactly are these optimizations implemented? Let's take an in-depth look at the core technologies behind them. First is DD's technology. Simply put, we store a complete digital sample of a sine wave in memory. A timer then triggers DMA at fixed intervals. DMA acts like a porter. Each time it's triggered, it fetches one sample from memory and sends it to the DMA, which converts the digital signal into an analog voltage signal. This cycle repeats continuously, generating a steady sine wave. The advantages of this method are high frequency accuracy, clean waveform, and great convenience for changing frequencies or waveforms. Next is synchronous sampling and DMA transfer. Synchronous sampling means the timing of signal acquisition is strictly aligned with signal generation, ensuring the sample data truly reflects the characteristics of the signal. As for DMA, or direct memory access, its role is to automatically store data into memory right after ADC sampling without CPU involvement. This frees up the CPU for other tasks, improves overall system efficiency, and enables higher frequency sampling. Here we present the key code for implementing high-speed synchronous sampling. On the left is the timer configuration, which we need to set to compare output mode to trigger DMA requests. On the right is the DMA configuration, where we specify the source address for data transfer, the ADC data register, the destination address, the memory buffer, and the amount of data to be transferred. These configurations form the foundation of the entire solution. Also included are the ADC configuration code, which involves setting the clock division ratio, sample and hold period, and sampling channels to enable high-speed, high-precision ADC sampling. Additionally, there is the true RMS algorithm, which performs square accumulation and average accumulation in a single cycle. The true RMS value is then obtained by subtracting the two accumulated values and taking the square root of the result. Thanks for watching.